last video, we introduced a criterion for determining whether a Lie algebra is solvable based on the trace of the operators in the adjoint representation. And in this video, we're going to do something similar, except for determining whether a Lie algebra is semi-simple. So with that being said, let's look at something called the killing form. So that's kind of the overarching construct we'll be using in this video. And so let L be an arbitrary Lie algebra. If x and y are elements of L, define kappa of x comma y to be the trace of the operator add x times add y. So of course add x and add y are elements of GL of L, and so the trace is something that makes sense. And so kappa is a symmetric bilinear form on L called the killing form. And so we see it's symmetric right away by the fact that trace of add x add y is equal to trace of add y add x. And we see it's bilinear by the fact that trace and adjoint are both linear operators. And so that is kind of that's the killing form. It's just this symmetric bilinear form. But it has this additional nice property, which is that it's associative in the sense that kappa of x bracket y with z is equal to kappa of x with y bracket z. And so we have this kind of, we can shift the bracket over. So it's not really associativity, but it looks like associativity. And so this follows immediately from the identity we saw last time, where trace of a bracket b times c is equal to trace of a times b bracket c. We can do this by simply taking add x to be a, add y to be b, and then add z to be c. And we get our identity here of associativity for the killing form just by the definition of the killing form. And so let's look at a quick lemma regarding the killing form. So let I be an ideal of a Lie algebra L. If kappa is the killing form of L and kappa sub I is the killing form of I, where we view I as a Lie algebra in its own right, then kappa sub I is equal to the restriction of kappa to I cross I. And so we won't be using this lemma in this video, but it will be useful later on, and so I'll just follow the book. And so the proof of this is pretty straightforward. Okay, so if you let's just take a step back to linear algebra. If you have an operator phi from V into W, where W is a subspace of V, then the trace of phi is equal to the trace of phi restricted to W. And this is pretty easy to see. If you take a basis beta for W and then you extend it to beta prime of V, we have the matrix of phi in the beta prime basis looks something like this. You have the beta chunk here, and then you have everything else. And then you have the beta chunk here, and then you have everything else, right? So it sends V into W, right? So if we partition this up into blocks, if it sends V into W, then anything else outside of beta has to get sent to 0. So we have this thing here, this block here is 0, this block here is 0, and then of course you can always send these things into W, so this can be whatever you want, and this can be whatever you want. And so this is the matrix of phi in some basis, right? And so we see immediately that the trace of phi, right, because it doesn't depend on beta, is equal to the trace of A, which, because 0 doesn't contribute to the trace, and so this is simply the trace of phi restricted to W, right? Because beta spans W. And so how does this relate to our Lie algebras? Well, so let x and y be elements of an ideal, right? First of all, add x times add y is a map from L into I. Right, this is easy to see by the definition of ideal. The first y does the job itself for you, and then the add x is just going to send I back into I. And so we have this similar setup where we have L is being sent into one of its subspaces, I. And so the trace, so the killing form, right? Killing form of add x, or of x and y, is equal to the trace of add x, add y. Right, and so really this is the restriction of kappa to I cross I, because x and y are elements of I. And so is this equal to the trace of add x times add y? And so this is, by the above fact, add x times add y restricted to I. And then, of course, add x and add y, once we've restricted the product to I, that's got to be the product of add x restricted to I and add y restricted to I, which we can restrict because x and y are elements of I. So this is equal to trace of add sub I of x times add sub I of y. And, of course, this is kappa sub I of x comma y. Okay, and so we have our lemma. So it's nice in the sense that we can just take our kappa for the algebra and we can send it down to its ideals pretty nicely, which is not always the case for bilinear form on subspaces. Okay, so now let's move on and let's take a closer look at the killing form. Okay, so let H be a symmetric bilinear form on L, and we'll start generally and then we'll look closer at the killing form. So we have something called the radical of H, and this isn't to be confused with the radical of a Lie algebra. And so the radical of the bilinear form is all vectors in L such that x is orthogonal to everything in L, right? And so I'm saying orthogonal because H of x comma y is equal to 0. So the 0 vector is always an element of the radical, which can be seen by bilinearity. And the radical is in the case that kappa is H. So in the case that we're looking at the killing form, the radical of the killing form is actually an ideal. It's not just this collection of vectors. And so it's easy to see this because of the associativity of kappa. So if we want to show something's an ideal, right, that means for all x in the ideal, so we'll say S is equal to rad kappa. So for all x in S and for all z in L, we should have that x bracket z is also an element of S, right? That's what it means to be an ideal. So let's see if this thing is an element of the radical. So that means it has to satisfy this condition. So that means trace, or let's just not invoke the trace. We already have our associativity of kappa. So kappa of x bracket z with y, so for any y in L, we have that kappa of x bracket z with y is equal to kappa of x with z bracket y. This is the associativity of kappa that we saw, right? But x is an element of the ideal, so z bracket y is just some random vector in L, and so because x is in the radical, this means this is equal to 0, and so that means this thing is 0, and so this implies that x bracket z is an element of S. So this is important. We have that the radical of the killing form is an ideal, and that will be important for our criterion on semi-simplicity. And so, in particular, we say that a bilinear form is non-degenerate if its radical is equal to 0. So it just contains the 0 vector. And so the natural question that follows from this is there an easy way to deduce if a bilinear form is non-degenerate? And the reason we're looking at all of this is because we are actually going to relate non-degeneracy to semi-simplicity. That's the goal. So that's what we're considering, the radical and non-degeneracy, and considering whether rad k is an ideal or not. And so the easy systematic way, I wouldn't say easy because there's still some work involved, but a way to deduce if H is non-degenerate is to consider the following approach. Fix a basis beta for L. So x1, x2, dot, 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 xm, right, for L. Right? Then we can define the matrix of the bilinear form with respect to beta as follows. You just take pairwise vectors and then you throw them, you throw the results in the corresponding spot in the matrix. So what that looks like is you have this matrix H of xi comma xj, where I comma j equals 1 to m. So the I thrown in the jth column simply contains the bilinear form acting on xi comma xj. And so by bilinearity, we can actually deduce the bilinear form on all the vectors from its matrix because these vectors span the space. And so how does this help us? Well, if this matrix, if H sub, or let's actually say it this way, H is non-degenerate if and only if, so if and only if H sub beta is invertible. So if it's not invertible, it's not degenerate, it's not non-degenerate, and if it is invertible, then it is non-degenerate. And so let's take a look at an example of this. Just a quick example. So of course, everyone's favorite example is SL2C, and so I've reconstructed the commutation relations here and how they can be identified with a subalgebra of GL of V for two-dimensional complex vector space. And so the question is, what is the matrix of kappa with respect to beta? So really, we're asking what is kappa in the beta basis, right? Of course, we want the beta basis because this is, I would argue, the easiest basis to work with because of how nice these actions are with respect to the adjoint, right? And so, of course, kappa, right? Recall kappa is equal of x comma y is equal to the trace of add x, add y. So let's deduce what add x. Let's deduce what add e, add h, and add f are, right? So we have add e, right, is going to be, well, we just had to determine its action on the basis. So add e acting on e is going to give you 0, so that's 0 here. E acting on h is going to give you 2 times e, so that's going to be 2, 0, 0. And then e acting on f is going to give you 1. So this is going to be 0, 0, 1, right? And now let's look at add f, or add h. H, oh, something's not right. This should be a -2, right? Because the commutation relation says h bracket e is 2e. So we swap it around. So now let's look at h. H acting on e is 2e, so this is 2, 0, 0. And then h acting on itself is 0. And then h acting on f is 0, 0, -2. And then lastly, add f, right? So it acting on e is going to give you -h, so it's 0, -1, 0. Oh man, I messed this up. This should be a 1, shouldn't it? So this is a 1, and this is a 0. And so this is 0, -1, 0. And then this is, so f acting on h is going to give you minus 2f. And so that's going to put a 2 down here. And then, of course, f acting on itself will give you a 0. Okay, so there's a nice kind of a symmetry thing going on here. And so, of course, now if you want to compute the matrix, well, the matrix looks something like this. It just looks like this. Kappa of e comma h, what am I saying? Kappa of e comma e, kappa of e comma f, kappa of e comma h, and then kappa of f comma e, kappa of h comma e, and so on. Kappa of f comma f, kappa of f comma, nope, kappa of h comma f, kappa of, oh man, what is this? F comma h, and then kappa of h comma h. All right, so this is what the matrix looks like in the beta basis. And so I'll leave it to the viewer to actually do this computation, right? It's just some matrix multiplication. And you can deduce that the determinant of this matrix is not 0 when the characteristic of f, and since we said it was SL2C, we don't have to even worry about characteristic. But in general, we get that if the characteristic of the field is not 0, SL2F's killing form is not degenerate. So SL2C killing form is not degenerate. And so you actually don't have to multiply the matrices out. Another way to do it is to actually just consider which vector, like these commutation relations are so nice. And so you can just consider what does this vector do when you act on the basis vectors, and then you can see which ones are stabilized, right? And so which ones are stabilized are going to lie in the diagonal, and from that you can deduce the trace. So anyways, that's just a quick detour. I always like to look at SL2C as an example. And so let's come back to how this relates to semi-simplicity, because that's the goal, right? We want to relate the killing form to semi-simplicity. And so recall the definition of semi-simplicity, right? So L is semi-simple if the radical of L is equal to 0. That is, and the radical of L is the maximal, it's unique, maximal, solvable ideal, right? And this actually contains all solvable ideals, because if it didn't, right, let's say there was some ideal I that was not contained in rad L, that's solvable, then you could just add the two, right? And since this is maximal, right, the sum of these two things is going to be a solvable ideal. And so by maximality of rad L, this is equal to rad L, and so this forces I is contained in rad L, right? So this contains all solvable ideals. And so, so in particular, we have that this condition here, this condition, is actually equivalent to saying that L has no abelian ideals. And the reason this is the case is simply because we can look at it in both directions, right? Of course, an abelian ideal is solvable, so it's contained in the radical, okay? So that's kind of one direction. And so in the other direction, right, the radical would include any such ideal of L, right? Because, sorry, let me rephrase that. The radical, you can construct any such abelian ideal, because let's say you had a non-zero radical, right? So suppose you had a non-zero radical. Had a non-zero radical. Well, then this radical is solvable, right? It's a maximal solvable ideal. So that means there is some n, so let's write this, rad L, so then when you do the derived series enough time, remember this to the nth power, this is equal to 0. And so suppose this is the smallest such n, then rad L to the n minus 1, right? This thing here is going to be abelian, and it's not 0 by assumption, by a restriction on n. And so if you have a radical that's non-zero, then you have an abelian ideal, and of course any abelian ideal lives in the radical. And so what we see here is that L is semi-simple if rad L equals 0 by definition. Alternatively, if you can show that L has no abelian ideals, then L is semi-simple. And so this is the reason we stay it this way is to show our criterion for semi-simplicity, which is what we'll use in the proof. So let's go all the way to the top and introduce our criterion for semi-simplicity. A non-zero Lie algebra L is semi-simple if and only if its killing form is not degenerate. And so that's why we spend all of that time looking at all that stuff. So let's actually prove this result. So let's look at the first direction, okay? So suppose that rad L is equal to 0. So this means L is semi-simple, right? This is not to be confused with the radical of the killing form. So suppose rad L is equal to 0. Let S equal the radical of the killing form. By definition, right? By the definition of this thing, we have that trace of add x, add y is equal to 0 for all, all x in S, and for all y in L, right? And in particular, for all y in the commutator, or excuse me, the derived algebra of S, right? Because this is contained in L. So this is obviously true. And so now this is where we need our conditions on the field. Now we can actually apply Cartan's criterion. We have that add S, right, as where we view add as an operator on L. We have that add S is solvable. by Cartan's criterion. And so this comes, that's why we consider this thing, right? Because that's what Cartan's criterion says, is that if the trace of add x times add y is equal to 0 for all x and s, and for all y and s bracket s, then add s is solvable, and then it follows actually that s is solvable, and so s is solvable, right? This was the corollary we saw at the end of the last video. So s is solvable, and so because s is solvable, and it's an ideal, it has to be contained. S isn't a solvable ideal, so that means S is contained in rad L, which is equal to 0, so we deduce S is equal to 0, but S is the radical of kappa, so rad kappa equals 0, so kappa is not degenerate. So that's one direction, or let's say non-degenerate. Non-degenerate. So now let's look at the other direction. So let's change colors for this. Let's go on to red. Okay, so this was one direction. Now we want to show that if the killing form is not degenerate, then our Lie algebra is solvable. So now, suppose rad kappa, our radical of the killing form, is equal to 0. So this is not the radical of L. I'll explicitly state that over and over again because it's easy to confuse the two. So we want to show that L is semi-simple. So rather than showing that the radical is 0, we're going to use our equivalent condition that we just saw, which is to show that every abelian ideal of L is 0. And in particular, the way to do that is to show that it's contained in S, but S is 0. So suppose, right, take x element of I and y element of L, right? Then the map add x, add y is a map from L, so it goes from L into I, right? So the y is just some random vector in L, so that's just going to send L into L, and then x is going to send L into I because x is in the ideal, right? And so that means the operator add x, add y, add x, add y, which is equal to add x, add y squared, is a map from L into I. And now since this is an ideal, when you take add y acting on this, it's going to send it to I. And then when add x acts on I, it's going to send it into I, bracket I, right? But I bracket I is actually equal to 0 because of our assumption that that the killing form is 0, right? Because of this add x, add y. So, anyways, where are we? Oh, excuse me. That's not y. That's not y. This is 0 because this I is an abelian ideal. I is an abelian ideal. I guess I didn't actually say that. So I is some arbitrary abelian ideal. And so add x, add y, right, I bracket I is going to give you 0, and so add x, add y is a nilpotent operator. So this is a nilpotent operator. And so what do we know about the nilpotent operators? Well, their trace is 0. So what we have is that kappa of x comma y is equal to 0 because this is also the trace of add x, add y. Right? And so what we have is that the killing form on everything in the ideal, so for any arbitrary element, so let's actually explicitly write this, for all x element of I an arbitrary abelian ideal, for all y in L, right? We have that kappa, we just saw here that kappa of x comma y is equal to 0. So kappa of x comma y is equal to 0, so this means that x, by the definition of the radical, is an element of S, but the radical of the bilinear form, right? And so what we see is that x is an element of S, but what are the elements of S, right? It's just 0. So what we have is that every abelian ideal is 0. And so that shows the other direction. This means that L is semi-simple. And so what we see from this actually is that the radical of L is always contained in the radical of kappa. And so we have this is our criterion in particular. So a non-zero Lie algebra is semi-simple if and only if its killing form kappa is non-degenerate. So this is a very nice criterion because, as we saw, we can always, if we can fix some commutation relations, we can deduce the matrix of kappa once we fix a basis for L, and then we can compute the determinant. And if we can show that kappa is non-degenerate just by computing this number, we get for free that our Lie algebra is semi-simple, provided it is over an algebraically closed field of characteristic 0, right? Where did we use that fact? We used it here in Cartan's criterion. So be careful if you're over an arbitrary field. So anyways, that concludes this video. Thanks for watching. We will move on to the simple ideal decomposition of a semi-simple Lie algebra in the next video.